Hello, my name is Luke and I'm back with another video for this PyTorch tutorial series. In this video, we're looking at the much requested vector quantized variational autoencoder. If you're new to the channel, all the code you see here is available in my PyTorch GitHub repo, link in the description. And if you're new to the channel, I have a whole bunch more videos that are a part of this playlist. So what is a vector quantized variational autoencoder and how is it different from our vanilla or basic variational autoencoder? Well, we've already seen our basic autoencoder, this neural network design where we have some network that consists of an encoder and a decoder, where the aim is to take some input through our encoder, usually compress it to some latent code or latent representation, which is just an abstract intermediate representation of our data, and then have our decoder trying to reconstruct the input to the encoder on its output. The idea here is that we're compressing our input into some intermediate latent representation. We then looked at variational autoencoders where we have our encoder and our decoder still, but our encoder doesn't produce the latent vector or latent representation directly. What it does instead is produce the parameters of a normal distribution per input, and then we sample from that distribution to produce our latent representation. And we talked about why we did this. We're trying to create a regularized representation. We're trying to create a smooth representation or latent space, because we saw how we had these issues with a vanilla autoencoder of these dense clusters with sparse regions of nothingness in our latent representation. And we saw while we can't sample or generate new images from our variational autoencoder, it does produce, as I said, these nice regularized latent representations that we can then use for other tasks. With our vector quantized variational autoencoder, we're doing something pretty similar, except instead of using a continuous normal distribution per value in our latent vector, we're going to instead use a discrete multinomial or categorical distribution per latent vector. So we're going to chunk up our latent representation into chunks of vectors, and we're going to sample from some discrete distribution to get each one of those chunks. So to better explain what I mean, imagine we have our encoder here that is producing our latent representations from our image, and we have our decoder, again, which is going to reconstruct from the latent space. Typically here we have some, maybe just a 2D vector of values. With our vanilla variational autoencoder, again, we produce a mu and a standard deviation per value. So one per value in our latent vector. And then we would sample from that, and we saw the reparameterization trick and et cetera, in that other videos, how we actually implement this. Now what we're gonna do with our vector quantized is we're going to chunk up this representation into same-sized individual vectors. So I haven't quite given equal number here. So if we imagine we have 1, 2, 3, 4, 5, 6, let's imagine we chunk this up into vectors of size 2. We have 3 of them. What we want to do is we want to sample each of these vectors from a known set of vectors. So with our multinomial or categorical distribution, this is a discrete distribution. All right, and it might look something like, we imagine our probability distribution, it might look something like, and as I'll get into, we're not directly producing these distribution, but essentially this is what we're implementing. So for each of these, what we want to do is we want to map it to one of sort of these values that we have. So in this case here, we have, say, 1, 2, 3, 4 different categories that each of these discrete chunks can be a part of, and we want to assign it to one of those. Now what that assignment looks like in our vector quantized VAE is, for each of these indices here, a value in a code book. So here we've got 4, so 1, 2, 3, 4. So this is going down the rows, 2, 3, 4. And so what we want to do is we want to map each of these chunks to one of the values in this code book. Each of the values in this code book are just what each of these categories are. So the first category is this vector, second is this vector, et cetera. So by doing so, we're turning some continuous representation from the encoder into a discrete representation, because each one of these chunks has to be one of these from the codebook. You might be thinking, why aren't we just, producing the probabilities here? Am I doing a softmax? And then from that sampling from this codebook, well, again, it goes to the fact that we can't backpropagate through a random sampling. We talked about this in the variational autoencoder. We had to do this reparameterization trick. This, in essence, is that sort of reparameterization trick, but for this discrete vector quantized case. So how do we do this assignment then? Well, what we do instead is each of these vectors or these chunks from our latent representation, we basically find which of these from the codebook it's closest to in just like a Euclidean sense. So we just find the Euclidean distance from each of these chunks to each of the codebook vectors, and then we reassign that chunk from the codebook to be that chunk from the actual latent representation. So we do a replacement. So if I just change color, what we get now is, say, maybe this first one was 2, Right, so this is now replaced with 2. The next one was replaced with 3, and maybe the last one was replaced with 1. These all come from the code book, just finding the one that it's closest to. And then this is what we then pass to the decoder to actually decode. Right, that's our decoder. And then we get our output image. Okay, but now you might be thinking, well, if all we're doing here is finding the distance and then getting the index of that and passing it through the decoder, well, we also can't backpropagate through that. So how do we rectify this? Well, in practice, we don't actually just pass it straight from the codebook to the decoder. We also do a kind of reparameterization trick where we're going to mix the output from the encoder with this codebook. So again, if we have those 3 little vectors or 3 chunks from our encoder, and also the ones from our codebook that we've selected, I'm going to call these E, and let me just call this B for codebook. And what we're going to do is, using E and B, is construct our latent representation R, and that's just going to be equal to E plus B take E. So you can see if B and E are exactly the same, we're going to get 0 here, and then E is just going to be E. But if there's any difference, we're going to add that difference onto E, and we're just going to get B back. So you can see if I expand this out, E take E is just B. So we're just going to get our codebook vector. You might be asking, Luke, well, why are we doing this then if we're just going to get B back? Well, the magic happens when we backpropagate through this. What we do in practice is, during the forward pass, we detach what's inside these brackets here, B take E, and we treat it as just a constant. So R becomes E plus C. So by detaching this from our computational graph, this is just treated as a constant in the backpropagation. So if we then take the derivative of with respect to E, this, hopefully, as you can see, is just going to be 1. So this reparameterization here with this difference here detached or treated as a constant is just a pass through of the derivative from the decoder straight into the encoder. So the encoder will get some derivatives from the decoder by doing this sort of weird reparameterization. But each of the chunks of our representation are just going to be chunks from the codebook. So it's just a clever way of doing this. But of course, we actually need to still update the vectors within our codebook. We're not just going to keep them as whatever we randomly initialize them as. We're going to update them so that they learn to be some good codebooks that are useful for our decoder / encoder to use to actually encode the input image. So how do we do that? Well, we basically just construct a loss on the codebook vectors that were selected to make them closer to the chunks produced by the encoder. And that's just going to be a mean squared error loss, nothing too complicated. We're going to put a loss on the codebook vectors that we selected to push them towards the output of the encoder. So our vector quantized loss is going to be B take E, and then, mean squared error. Simplify that to just squared. But what we don't want to do here is actually move E towards B, because what's going to happen here is that they're kind of just going to collapse together to potentially all being the same value or 0 in practice. So what we do here is we actually detach this as well. So I'm just going to do a little B here. So we're going to detach this so gradients don't flow from this loss into the encoder. But we don't want the encoder chunks to sort of do whatever they want and potentially explode in value, like really pushing each other away, which is similar to what we see if we were to just introduce a small amount of noise into a regular autoencoder. The actual representation magnitudes tend to just explode in size. And so we're going to actually include another loss pulling the encoder chunks towards the codebook. And it's essentially going to be exactly the same as this loss here. Again, B take E squared. But what we're going to do is we're just going to actually scale this down by some parameter here. I'm just going to call it lambda. And again, here we're going to actually detach B and detach. So no gradients from this part will flow into the codebook vectors, but again, it's over here. And this is going to be, this lambda here is going to be some value less than 1. Typically, it is just 0.25. There's going to be a little bit of a loss pushing the encoder chunks towards the codebook, but not enough to sort of collapse it. Right? So we're scaling it down such that the loss from the decoder reconstruction that's backpropagating through the decoder, through this step here, into the encoder output is going to be larger than this loss here, which we are calling the commitment loss. Trying to get our encoder to commit to one of the vectors that is in the codebook, not just choose whatever it wants. So the reconstruction loss from the decoder is going to try and push the encoding vectors or encoding chunks to whatever it wants to be. This commitment loss is also going to slightly pull it to one of the codebook vectors that already exists, while this codebook loss is again trying to make sure that those codebook vectors are useful. Ultimately though, what informs the structure of the latent space is the reconstruction loss and is the backpropagation from the decoder through this reconstruction of the representation space into the encoder. The quantization loss pulling and pushing the codebook vectors in the encoding output to some discrete set of chunks that are going to be useful. Let's hop back into the code and see what that looks like in PyTorch. So for simplicity, I'm just going to use the MNIST dataset again. Though this code does work with sort of any other dataset, you will have to sort of change the scale as we've seen before. The encoder and the decoder for this network look pretty much exactly the same as our variational autoencoder. The important part is this vector quantizer block. And this is what does the vector quantization, finding the distance between each chunk of the encoder and each codebook vector, and it also computes the losses as well. One thing to point out here is that in my example here, we've got like this flat 1D representation for our latent space, but for images, what we tend to do is actually use a 2D representation. What I mean by that is basically we're not flattening out that 2D feature map from our convolutional neural network. We're keeping it as a 2D feature map. So we're going to have some 2D feature map like this. Let's say it's just a 3x3, and it's going to have some depth or some number of channels rather. So hopefully you can imagine what I'm saying there. So it's going to have some depth. So that's our number of channels. And then we have our width here and then our height here. And just so you remember, in PyTorch, that looks like channels by height by width. And what we're going to say is that each vector or each chunk here is actually just going to be a single location spatially. And the number of dimensions is just going to be the number of channels. So we're actually going to permute and flatten this to be of shape height width by channels. So we're going to have height width. So this is 3x3. So that will be 9. And let's imagine this is 4 channels. So it'd be 9 by 4. So our latent representation will be made up of 9 vectors, each size 4. Again, that's for this example here. The actual code example, we'll see what actual values we use. Hopefully you can see this is what we're going to be doing for our image convolutional neural network. So what that looks like in code, we have our inputs. This is just the output of our encoder, right? Again, it's going to be batch size by channels height width. And we're going to permute that. So we go from batch size channels height width to batch size height width channels, as we saw. And then we're going to flatten that out as we talked about. So batch size height width channels. And we're actually going to make it batch size by multiplied by height by width by 1 by channels. So to do this quantization and find the distance between each one, we're going to basically put them all on the batch dimension and effectively have it as batch size height width by channels. And we're going to use broadcasting in order to find the distance from every single output chunk to every single codebook vector. So it's actually going to be, again, I'm just going to use n here. So the total number, which is the number of instances in our batch times the height and width, which is the number of vectors per instance in our batch, by 1 by channels. And we introduce this additional empty dimension, as I've talked about before, so that we can do the broadcasting. Our codebook vectors are going to be in this nn.embedding. So we've seen nn.embedding before, the way of constructing a whole bunch of embeddings that we can then select an index. And you can see to calculate the distances, we take that flatted input and subtract it from the embeddings, the weights of the embeddings, and then we unsqueeze 1 to add a sort of batch dimension. So again, let's have a look at what that looks like. So that will be basically 1, we've added an empty dimension to the first one, by the number of codebook embeddings. So I'm going to call that M by C. So each vector is going to be the same length as the number of channels because that's how we've constructed it. Codebook size is the number, that's M, and then embedding dimension, again, that's just going to be the number of channels. And then if we broadcast this by doing the subtraction, the result will be N by M by. Right, and that's because of the broadcast. So I've written it out in the comments here as well, just so you can keep track of what the shape's going to be. So the asterisk here is multiply, not by. So again, that's our batch size, height, width. Here I've used N instead of M. I know it's a bit confusing, I apologize. The next step is to find which of those distances is the smallest. So for each chunk of the latent representation, we've calculated the distance between that and every vector in the codebook. Now we need to find the closest one. And we're going to use argmin because we want the actual index, not the actual distance. Again, let's go back. So what did we have? We had, let me just keep it consistent with my code, batch size, height, width, height. I know it was M, but now it's N. That's just the number of codebook vectors. Codebook. So for every single instance in our batch, it's going to have height, width, chunks, and then for every single one of those, it's going to have a distance between it and every single one of the codebook vectors. So there's going to be n distances, and we now want to find the index of which of those codebook vectors it was the closest to. So the result of the argmin will just be batch size, height, width. So for every chunk in every element in our batch, we're going to have some index which says this is the codebook vector that it is closest to. And here you can see I unsqueeze it as well. I don't think I actually need to do that, so don't worry about that too much. Once we have those indices, we then index the embedding, and then we get the codebook vector that the encoder chunk was the closest to, and then we reshape that to be the input shape after we did the permute. So it's going to be batch size, height, width, channels, and that's just because of the shape. So remember, this is going to return before the reshape. It's going to return batch size, height, width by what? The size of the size of each of those vectors, which was CER channel. This can't be reshaped directly to the original input. It can be reshaped to batch size, height, width, channels, and then we need to do the sort of 3D transpose or the permutation to get it back to the original batch size by channel, by height, by width, which is what the PyTorch convolutional layers need. So we can see that here, the quantized view output shape. And then we do that final permutation here when we return the actual quantized output. So I don't do it here, I do it down. And that's just because I do that actually reparameterization with inputs, and inputs I've just got it here as the result of permutation originally. You can structure this in a different way. In any case, what we're going to do next is just construct those two losses. Again, all it is a mean squared error. So that commitment loss is just going to be the quantized, so the reconstructed using the codebook vectors, detached, not backpropagating through this, and the original inputs, so the output of the encoder. And then again, the quantization loss is going to be, we're now going to be backpropagating to the embedding or the codebook and detach the inputs. And then we're going to combine those. It's just the quantization loss plus the commitment loss multiplied by the commitment cost, which again is at 0.25. Again, we're just going to scale that down so we're not forcing the encoder to commit to one of the codebook vectors too hard. And then, as I said, we're going to reconstruct that quantized representation using the quantized and the original inputs. We're going to do our detach, so that's just going to be treated as a constant. As we've talked about before, that's how we get our quantized representation, which, as I said, we're then going to permute to be the original shape from the input before I do this permute here. I'm actually going to also return the indices from the argmin so that later on we can use these. I'm going to skip over the construction of the encoder and the decoder network because, as I said, they are very similar to the VAE, but we can actually look at the overall network structure. We have our encoder, the decoder, and the vector quantizer. In our forward pass, we encode the input image, and we pass that through our vector quantizer, get the VQ loss and the quantized representation, and we return all that, pass the quantized representation to our decoder to get a reconstruction of the original image. So as I said, we're just using MNIST dataset here for simplicity. Let's see how we can create our model. We're going to be using a codebook size of 32. There's going to be 32 vectors in our codebook. We're going to have a vector size of 10. So there's going to be 10 channels. Each codebook vector, each embedding chunk is going to be size 10. And we're just going to be training for 50 epochs. You can see, yes, the commitment cost there is just 0.25. We have our optimizer, our mixed precision scaler, and we're also going to have a learning rate schedule. So you can see, very simple data set, only 500,000 parameters. And as per usual, I've already trained this. So we can see our reconstruction test and train loss has gone down. So this is just a mean squared error on the actual input output. We can see our quantization loss, right? That's the quantization of the codebook, and also the commitment loss for our encoder goes down very quickly at the start and stays pretty low. So we can see some testing. We put our network into evaluation mode, go back to our network. You can see that in evaluation mode for our vector quantizer, we skip this reconstruction and we just use the raw quantized vectors. And you can see our reconstructed output looks very similar to the input. So we've trained it correctly and we've got our quantized embeddings, and you can see our indices here. This is for the whole batch, but let's just select the first one. Right, so these are all of the indices from the codebook that make up our representation. We should have around 64. Again, that's because we skipped over this a little bit. Our encoder only downsamples it 2 times. So our representation is going to be that 10 channels and then by 8 by 8. So we're gonna have 64 actual chunks. Now you might be asking, okay, well, that's cool. We can encode, represent some input as a discrete set of chunks from some codebook. But Luke, why is it so good that we can represent an image or some other input as a collection of some discrete set of codebook vectors? Why is it useful that we're now using a discrete distribution instead of some continuous normal or something else distribution? Well, it's because of the flexibility of discrete distributions. We can represent our distribution as a multinomial or some categorical distribution. Well, these discrete distributions can kind of approximate any sort of distribution. So it can be very difficult to get our output of our neural network to produce some arbitrary distribution? Normally we just go with a normal distribution because we can produce a mu and a standard deviation. But what if we have some multimodal distribution, some other complicated distribution, exponential, blah, blah, blah. We just don't know what distribution. Well, if we allowed our network to produce a discrete distribution, then that can kind of approximate our distribution. So if we imagine we have some distribution that looks like this, well, if we have some number of chunks, we can sort of quantize this. We can represent it as some discrete distribution instead. So instead of having any sort of vector that sort of follows this sort of probability distribution, we can chunk it up and say, okay, we're now only going to have 1, 2, 3, 4, 5, 6, 7, 8 vectors that you can choose from, right? Not a continuous set. You can sort of approximate this distribution. You might be saying, okay, well, that's very good, but still, what is it useful for? Well, one thing that is shown in the original VAE is that now that we've got this set of discrete chunks, we can use some sequence to sequence model to generate this sequence of chunks. And at every time step, our model is just going to produce like a softmax distribution over the possible codebook vectors. And then we're just going to sample from that distribution, again, which approximates our whatever distribution it should be. So we can sequentially generate that whole set of 64 in our case, discrete chunks, and then decode and hopefully generate an image. You might be asking, well, if we've got this set of indices, why can't we do something like a segmentation model where at every single spatial location we have our softmax distribution and just sample from each of them? And that way we can do it in one step, not as a sequence. Well, the issue comes from the fact that each of those samplings is going to happen completely independently from all of the others. If we have that 2D representation, and again, I'm just going to treat it as a 3x3, not our 8x8. And again, we have some probabilities for our channels like we do with our segmentation. And we're going to sample, each of these chunks independently. We will get a set of quantized vectors and we can decode that. The problem is that there is some correlation between what each of these chunks should be. We haven't escaped that problem from the original VAE, right? Where we had this normal distribution, each value within that vector, we were trying to treat as independent, but there was always going to be this correlation. There was always going to be this structure in the latent space. Obviously, because the images are structured, the representation is going to be structured, there's going to be a correlation between the values. Just like if we were to sample from the latent space in original VAE and try and decode that, we just kind of get random jump. If we were to do the same all at once with all of those discrete distributions, and then try to decode that, we're also just going to get junk. What we could have done with our original VAE, for our vanilla one, is we have, let's just imagine it flat. What we could have done is, with a sequence-to-sequence model, randomly sample this first value here, put that into some model, and then try to predict this next value here, and, not just directly. Maybe we would try to produce a mu and a standard deviation, and then we sample, right? Sample from that, we get our Z, and that tries to predict this next value here, and we sequentially build up the representation, and we can do that, but again, we're assuming that the output distribution here actually is a normal distribution and not some more complicated distribution, which is harder for us to model, or harder for us to even know what it is. So what we're going to do is not only use this discrete distribution, but also do this sequential sampling. Now, why this sequential sampling works and not the one-step sampling is because there is, again, a correlation. The actual distribution isn't for each of these spatial locations independently. It's for the whole representation. What that means is that there's a joint distribution between each of the vectors in my quantized or each of the values in my vanilla VAE. So it's not just independent distributions, it is a joint distribution. There is a correlation between them. And that's very hard to model, especially for very large dimensional spaces. But we can construct or sample from a joint distribution by sequentially sampling from the marginal distributions, or rather the conditional distributions. Now, I'm not going to go into this in too much detail here, but if you want to look it up, it's called the chain rule. Not of derivatives, but of probabilities. Right, the chain rule of probabilities. So you can look it up on Wikipedia. Basically, here's a simple example. We have this joint distribution here, and we can get that by having the conditional distribution of x given y multiplied by probability of y. So we have this marginal distribution of y. If we multiply that probability by the conditional distribution of x given y, that gives us the joint distribution. It expands to any number of random variables. So for this example here, we've got 3. So it's the probability, or the marginal of x1, multiplied by the conditional x1, x2 given x1, multiplied by the conditional of x3 given x2, x1. So here we randomly sample from x1. Given that, we're going to randomly sample from x2 given x1. And now we have x1 and x2. And then we can sample from the conditional probability of x3 given x2 and x1. And then that is equivalent to sampling from the joint distribution of all three. I know I've gone over that quickly, but hopefully that makes sense. That is basically how all of these sequence-to-sequence generative models work. Like our large language models, we break up our sentence into some discrete set of chunks. We generate a sample from the joint distribution of all those chunks by doing it sequentially and splitting them up into these marginal or conditional distributions. So how can we do that without VQ-VAE? Well, we can just construct a sequence-to-sequence model, such as a transformer, and use that to predict the next token in our sequence, like we did with our large language models, except our tokens here are going to be the sequence of codebook vectors. So we're going to build a causal decoder-only transformer. I've got a whole video on that already, so if you aren't familiar, you can check that out. But this is going to be essentially exactly what we've seen before, this causal decoder-only transformer model, except instead of vocab tokens, it's going to be codebook vectors. And everything is exactly the same. Because we've used our VQ-VAE to represent our image as this discrete set of embeddings or tokens, right? We can treat them as a sequence of tokens. And then because of this chain rule of probability, we can sample from that distribution sequentially. And then once we've done that, we can pass that through our VQ-VAE decoder and get an image out. Here we've constructed our transformer. We've got the number of embeddings as the codebook size +1. I'm going to introduce a start of sequence token so that our decoder knows when to start sampling the very first token, which is just going to be a marginal, not conditioned on anything. And it's just going to be a simple 4-layer network, 8 heads. The hidden size will be 256. So what we're going to do while training is with no grad, so we don't want to keep the gradient here just for efficiency. We're just going to encode the image and we're going to get those encoding indices. I'm going to shift them all up by 1. I can introduce a start of sequence token at 0. Technically, I could have just added it onto the end. But the input to our decoder only model is going to be that start of sequence token plus all of the other tokens in the sequence, except for the very last one, because once we've done 64 steps, we don't need to predict from the last one. And then the targets are just going to be the original indices. That's just doing that one-time step shift that we've seen before. And really that's all it is. It's pretty much exactly the same as we would do for our large language model. So again, I've trained this already. I've trained it for 100 epochs, so a little longer. And you can see our loss goes down. I have a learning rate scheduler, so it drops the learning rate. So maybe this could have actually trained for a bit longer. So it's potentially artificially flattening out because the learning rate is dropping. Okay, so how do we sample from this? Well, we do it in exactly the same way as our decoder only transform for language models. We start with our start of sequence token. We put that into a decoder only model, predict the next token in the sequence, take the last token, we can scale it down by some temperature, sample from that output, add that onto our input sequence, put that back in, and keep going until we've done our 64 steps. Here we always know it's going to be 64 because we have 64 chunks in our representation. We can just run that. Here you can see the actual distribution over the tokens for the very last token. So the very last token in the sequence, it's fairly confident that this token here, if we break it after the very first step, we should expect to see a bit more of a higher entropy distribution because there's multiple possibilities. So this is basically the distribution over tokens for the very first token, not conditioned on anything. Let's just remove that and get our sequence. Let's have a look at what we got now. There we go. We have our reconstructed images from the generated sequence. You can see they are actually images of our MNIST numbers, and we can, try again. Have a look at what we got now. So what I've just quickly added here is an example of what happens if we were to just randomly sample all of those embeddings instead of doing it the sequential way with a transformer. I thought people are going to be watching this and saying, okay, well, you've sampled through our transformer in the sequential way. Are you sure we can't just randomly sample those codebook embeddings and then reconstruct and decode? So in this case here, I've just randomly sampled a batch of 64, and there are 64 of these embeddings per batch. And then we pass that through the vector quantizer's codebook. So let's select the embeddings from the codebook, reshape, etc., and then decode. And what we can get is similar to what we see with a VAE. If it's not really regularized, it's just garbage. So you can see that by training our transformer to sample correctly from the right distribution sequentially, we do get samples that are actually from sort of true distribution of MNIST numbers. So there you go. I encourage you to play around with this, scale it up, swap it to the Cypher 10 dataset. That's pretty easy. You just need to change the actual dataset from MNIST to Cypher MNIST here. So just change that to the Cypher 10. And also you would scale up the actual network as well. 500,000 parameters really isn't enough for Cypher 10, even though it's pretty small. Increase the number of codebooks, keep the latent channels the same. The original paper does train with Cipher 10 with 10 channels, it is actually a little bit sensitive to the size of each of those chunks. Increase the codebook size, increase the width of the network as well to increase the parameter count, and try with Cipher 10. You might also want to increase the size of the decoder only transformer. But in any case, that's all I have for you in this video here. Hopefully you found that useful. Hopefully you found that interesting. Hopefully you've got a bit of a better idea of how these generative models and generative networks work. So if you enjoyed that, remember to like. If you're new here, remember to subscribe, and I'll see you in the next one. Thanks.